Hello everyone and welcome again to 1021 EET1021. Today's lecture is going to be on the topic of inductance. In fact, this topic is going to be covered in a couple of lectures, and this is the first lecture on the topic. Well, let's start by defining inductance. Inductance is the ability of a conductor to produce induced voltage when the current changes on the conductor. Induced voltage is the result of flux cutting across a conductor. This action can be produced by physical motion of either the magnetic field or the conductor. Recall when we studied the alternating current, we had learned that alternating voltages is induced on the conductor by the physical motion of the conductor through magnetic fields, cutting through magnetic fields, and in different positions where the conductor was cutting most of the lines of flux. That's where most of the voltage was induced on the conductor. So that is one way of generating induced voltage. The other way is when you already have a conductor through which changing current is going through. That changing current also produces, without moving the conductor, the change in current produced induced voltage as well. So the variations in current levels, or the amplitude of the current, induced voltage in a conductor, because the variations of current and its magnetic field are equivalent to the motion of the flux. In other words, the change in current, it also generates a magnetic field that is equivalent to the flux. So when the current is changing produces induced voltage without the need for motion of the conductor. So this ability is called self-inductance, or simply inductance. Induction by varying current results from the change in current, not the current value itself. The current must change to provide motion of the flux. And the faster the current changes, the higher the induced voltage. Here is an example. And if this is the sine wave of the current. So when we learn about alternating current, remember that it started from 0, it goes up to the maximum value of current, and at this point is where most of the current is changing at the fastest speed, and then it goes back to 0 and then go back into the negative values, and whenever it gets to the maximum negative value, that's where the current changes the fastest. So as we can see in this, if this is the behavior of a changing current on an inductor, if there is no current change, there is no magnetic fields generated or varying. As the current changes in value, more magnetic field is being generated. At the point C, for example, that's where the current changes the most. There's more current change per second right here. That's where most of the magnetic field is generated. Okay. The same happens when you go into the negative side of the behavior of this sine wave. So basically, the characteristics of inductance are important, but what we need to understand is that what generates the magnetic field from an inductor that has change in current is the change in current itself. It's not the movement of the conductor. This change in current could be the result of alternating current, and it can also be the result of direct or DC current on the inductor. Okay, alternating current changes from low to high, then back to zero, then goes to the negative side, and it keeps changing from negative to positive, negative to positive, negative to positive, and it changes values and also change in polarities. A DC circuit in which the current changes in value can also generate magnetic field or inductance. Even though on DC circuits the current does not change polarities, in other words, is always positive or is always negative. In DC circuits, the current changes from positive to negative, from positive to negative, and so on. But on DC circuits, the voltage or the current will flow in one direction only, but it can change in values. Okay, so it can go like a pulse wave, for example. It goes from zero to a higher value, back to zero, back to a higher value, back to zero, back to a higher value, and it stays on the same side of the zero line. So in other words, it could be it stays negative or it stays positive, but cannot change polarities. The symbol for inductance is L. And it comes from the linkage of magnetic flux. Okay, the formula to calculate the inductance is the voltage that is induced divided by the change of current with respect to time. The voltage is in volts, obviously, and the di dt, which means the change of current in amperes per second. That's how fast the current is changes every second. Henries is the basic unit for inductance. Recall that we have volts for voltage, amperes for current, ohms for resistors and reactance and impedance. So when we're talking about inductance, the units that we're going to be using is called the henries. And 1 Henry is 1 volt, is when 1 volt is induced with 1 ampere per second. In other words, the rate of change of the current, when we have current on the conductor that changes 1 ampere every second, that's when we have a 1 volt induced as a result of this inductance. All right, so now if we have this formula, we can always calculate how, if we know the voltage that is induced, and we know the inductance of the inductor, we can always calculate and find out how much the current is changing per second, or vice versa. If we know the change of current and we know the inductance, we can always calculate the voltage as well. Let's see if I can put up an example here from our textbook. All right, let's see. In this example, for example, we're gonna do the example 19. Okay, it says the current in an inductor changes from 12 to 6 amps in 1 second. Okay, 12 to 6 amps in 1 second. And they're asking how much is the di dt, which means that the rate of change of the current with respect to time, or the rate of current change in amperes per second. So to solve this problem, basically what we're going to do, if the current changes from 12 amps to 6 amps and in 1 second, all right, so basically to determine the rate of change per second is going to be 12 to 6. So what is the difference? What is the change? The change is, if it goes from 12 to 6, the difference will be 6 amps, right? Because 12 minus 6 will be 6 amps, and the time is 1 second. So this one will be 6 amps per second, right? That would be the answer on this problem. Okay, so if it changes from 12 to 6, the answer will be 6 amperes per second. I did a typo here, but the actual problem says it changes from 12 amps to 16 amps, and the time is 1 second. Okay, so this the current on this inductor changes from 12 amps to 16 amps in 1 second. So they want to know what is the dt, which is the rate of change of the current with respect to time. Or in other words, they're asking how many amperes per second. So in 1 second, which is the time, the given time, the change of the current was from 12 to 16. That is 4 amperes, right? So if it goes from 12 to 16, so the change will be 4. And the time it took to do that was 1 second. So the answer will be 4 amps per second. Okay? So this would be the rate of change of current per second. Another example, it says the current in an inductor changes 50 milliamps. Okay, it changes by 50 milliamps in two microseconds. Okay, so they're asking how much is the di over dt, which is the rate of change of the current with respect to time. So if the current changes by 50 milliamps, that means the actual change was 50 milliamps, right? So it could have been from 200 milliamps to 150, or from 100 to 150, or from 300 to 350. The change is 50 milliamps, and it took 2 microseconds. So they want to know what is di dt. Okay? So di means the change in current. So this one was 50 milliamps, and the time was 2 microseconds. Okay? They want to know how much is the di dt in amperes per second. Okay, so what we're having here is the following. If we have 50 milliamps, that would be 50 times 10 to the negative 3 amps. And 2 microseconds, that is 2 times 10 to the negative 6 seconds. Because we are looking for an amount that gives us in amperes per second, right? So we need to change from milliamps to amps, and from microseconds to seconds. And this is how we do that conversion, according to our powers of tens and engineering notation that we learned in the past. Okay, so 50 divided by 2 equals 25 times 10 to the negative 3 divided by 10 to the negative 6. That's going to give us 10 to the to the positive 3. Okay? 10 to the positive 3. because this one can also be calculated like that. If you want to get rid of the negative exponents, if it's in the bottom, you move it to the top and make it positive. If it's in the top, you move it to the bottom and change the sign of the exponent. That would be the same as this. Okay, 50 divided by 2 equals 25 times 10 to the 6 divided by 10 to the 3. That will give you 10 to the 3, right? Because that would be 6 minus 3 equals 3. And that would be 25,000 amperes per second. That would be the rate of change in this example. Okay, again, the current changed by 50 milliamps every 2 microseconds. So the change of current with respect to time would be 50 milliamps per 2 microseconds. So 50 milliamps is 50 times to the 10 to the negative 3 amps. 2 microseconds is 2 times to the negative 6 seconds. Okay, because we're looking for the units of henries, which is amperes per second. Not the only units of Henry, but the unit of the rate of change of current in amps per second. So if we do this division, we end up with 25 times 10 to the positive 3 amps per second. Okay. So, and according to our formula that we just learned about conductance, remember the conductance says that conductance equals the induced voltage divided by the rate of change of the current per second, right? So the problem, the example on chapter 9, the example 19.3 says, how much is the inductance of a coil that induces 40 volts when its current changes at a rate of 4 amps per second? So they're asking for the inductance. They say the voltage induced is 40 volts. And the current changes, in other words, the di dt equals 4 amps per second. Okay? This is the information that's given in the problem. They're asking, how much is the inductance of a coil that induces 40 volts when its current changes at a rate of 4 amperes per second? So if this is the formula, all we have to do is plug in the values that are given. So if they're already telling me that the voltage induced is 40 volts, so this is the voltage induced right there. That will be 40 volts. And the current changes, they say 4 amps per second. They are already in the correct units, amp per second. So that will gonna be 4 amps per second. So 40 divided by 4 equals 10. And that would be 10 volts seconds over amps, and that is the henries. So that would be 10 henries, right? That would be the answer to this problem. So if the voltage induced is 40 and the current changes by 4 amps every second, then the voltage divided by the change of current gives you 10 volts per second over volt times seconds over amps, and that is Henry. Okay, this is the same as having 10 volts over amps per second. The same thing. So when we solve this algebra for this fraction, we end up with 4 volt times the seconds and divided by amps, which is the basically units of Henry. All right. So let's do another example before we get into the next topic. Okay. If you look at your textbook and look for example 19.4. In this example, we're going to calculate the inductance. And they say, how much is the inductance of a coil that induces 1000 volts when its current changes at the rate of 15 milliamps in 2 microseconds, right? So here we go. Let's see. The given information is this. The induced voltage VL equals 1000 volts, all right? And the di dt, which is the rate of change of the current, they say the current changes by 50 milliamps per 2 microseconds, all right? The current change, and the time. The time, they say, takes 2 microseconds for 50 milliamps. So we can simplify this before we proceed with the problem. Let's simplify this and put it in amps per second, right? So let's say 50 milliamps is equivalent to, say, 50 times 10 to the negative 3 amps. And 2 microseconds is 2 times 10 to the negative 6 seconds. Now we have the units, amps per second, instead of microamps and milliamps and microseconds, right? So let's simplify this. 50 divided by 2, that would be 25, times 10 to the negative 3 over 10 to the negative 6, that's going to be 10 to the positive 3. Okay? Let's do this again. Okay, so remember, if we have 10 to the negative 3 over 10 to the negative 6, according to the powers of 10 rules that we already know, if the base is the same, we're going to copy the base, and because it's a division, we're going to subtract the exponent. So that would be negative 3 minus this exponent, which is negative 6. That would be 10 to the negative 3 plus 6, and that will give you 10 to the positive 3. All right? So 50 divided by 2 is 25. 10 to the negative 3 divided by 10 to the negative 6, this equals 10 to the positive 3. Okay? So the rate of change of the current per unit of time, it will be 25,000 amps per second. Now we have the right unit, right? Our formula calls for this. The inductance equals the induced voltage divided by the rate of change of the current in amps per second. Amps per second we have it here, so that's going to be 1000 volts is given. Remember, this is given in the problem. They give you 1000 volts and they tell you that the rate of change of the current is the current changes 50 microsecond every 50 milliamps every 2 microseconds. So when we change this to amps per second, we end up with 25,000, right? So that's going to be 1000 divided by 25,000. This is amps per second, and these 3 zeros cancel with these 3 zeros, and we will have 1 divided by 25, and now this is going to be henries. All right? If we divide by 1 by 25, we're going to have 0.04 henries. All right? Now, this one we can use engineering notation. If we move the decimal 3 positions over, we can say that this is the same as saying 40 millihenries. Okay? Let me recap this problem, review this problem again. The problem says, how much is the inductance of a coil that induces 1000 volts when its current changes at a rate of 50 milliamps in 2 microseconds. Okay, this is the change of the current. It's telling you that the current change is 50 milliamps every 2 microseconds. So you can write it like this, and then you simplify to get it into the units of amps per second. All right, and that will give you this amount, which is 25,000. this part right here was just a reminder of how to solve this type of powers of tens. So now we have the voltage and we have the change of the current per unit of time. So, and the formula says that the inductance equals the voltage divided by the change of current. So it's 1000 divided by 25,000 amps over second, and that would be 125 henries. If we divide by 1 by 25, we get 0.04 henries. If we don't want to use the decimals, we can always say this is going to be 40 millihenries. Okay, and again, this is the example 19.4 on your textbook. It's on page 581. All right, so let's continue here. So that is the formula to calculate the inductance, okay? The inductance is calculated by dividing the induced voltage by the rate of change of the current, the amount of current that it changes per unit of time, which will be the seconds. Another area that we need to look at is something that's called inductance of coils. The inductance of a coil depends on how it is wound, okay? And when you have a coil, the amount of inductance that you're going to be inducing from this coil can induce on other coils nearby or other conductors will be based on the number of turns of the conductor around the coil. It depends on the area enclosed by each turn. In other words, how wide the coils are. It also depends on the permeability of the core, what's inside the conductor, in what material is the conductor is wound on, and also depends on the length of the conductor, the length and the number of turns. Okay, here we go. This is what we're talking about, right? So now we have this is the formula for the inductance. Okay, if we go back, this is the formula for the inductance, one of them. Okay, the inductance can be calculated by the induced voltage and the rate of change of the current. However, if we don't have these quantities, we can also use this formula right here. Okay, and this is purely calculated from the characteristics of the inductor. Okay, so the formula says the inductance equals mu r times the number of turns squared multiplied by the area divided by the length, and then all this multiplied by this constant, which is 1.26 times 10 to the negative 6, and the units would be the henries. Okay, in this formula, the L stands for inductance. It would be this one right here. Okay, the mu, this mu right here, which in the formula is right here. Okay, this mu is the permeability of the core. Now the core being the material in which the conductor is wound around. Okay, some of the inductors don't have anything in there, so the core is made of air. The N in this formula, this N right here, stands by the number of turns, how many times the conductor is wound around the core. Okay, the area that they're talking about on this formula, this area right here, is the area of this of the inside of the inductor. In other words, if each turn is this, they're talking about the area inside the circle. So how much area each turn of the conductor covers. Okay, so in other words, if we make a cut here, if we cut this like that, so if you look at this cut from this angle, so you're gonna see a circle. So what is the area of that circle? Okay, the area of that circle, that's the area that we're talking about in here. So it's the area, and because this area, the units will be square meters. And L in the bottom, the little L right here, is the length, and the units will be meters. So the area is in square meters, the length is the distance measurement. Okay, so the length from here to here, okay, that is the length of the inductor. So if we need to find out what is the inductance that we can get out of the device like this, if we need to know what is the permeability of the material from which this is being built, okay, the number of turns this wire was wrapped around this the core, the area of each turn, okay, the circle, how much area each core, how big the turns are, and the length of the cord of the inductor, this length right here, right? So, and this number right here, 1.26 times 10 to the negative 6, this is a constant, okay? So this one will be there all the time, every time that we use this formula. It's just a constant value. So some of the typical values for coil inductance is like anywhere from 1 to 10 henries. This usually happens when the core of the core, this material right here, this material is iron, okay? But then we will be working with millihenries and microhenries depending on the material of the core, okay? For example, the permeability of air. For example, there is no metals in here. All it is just the wires, you know, turn around, you know, in rings like this. The air core permeability will be 1. Okay. The iron core, if this is a piece of iron in which the conductor is being wrapped around, then the permeability is much greater than 1, depending on the material. Okay, this quantity, this permeability is usually given in a problem. If it's not given, at least everything else is given, so you can figure it out. All right, so let's see. Formulas that we learned so far. Self-induced voltage, okay? This one right here basically comes from the formula that we had before, from here, okay? So if you look at this formula and you have the inductance and you have the rate of change of the current, you can always find the voltage by solving for voltage on that previous formula. All right, let me see if I can do it here on paper so you guys can see how this is. Some of you already have it, but let's see if we can do this. Remember the formula for the inductance, right? The inductance equals the induced voltage divided by the rate of change of the current with respect to time, right? So if we have the inductance and we have how much current changes with respect to time, then we can actually find the voltage. From here we can derive that the voltage equals to, if we multiply both sides by dITI, let's say like this, I mean dIdt, I'm sorry, okay? So if we want to find the voltage, all we got to do is multiply both sides by dIdt, which is the change of current with respect to time. Right? This one and that one cancel, and now that leaves you voltage by itself, so you can say that the voltage induced equals to the inductance times the rate of change of the current with respect to time. Okay? And that's where the formula comes from. This formula, okay? So the induced voltage is proportional to the inductance L. What proportional means? It means that they are, if one goes up, the other one goes up. If one goes down, the other one goes down. Okay? And it's also proportional to the rate of change. So the bigger the change, the more change happens with the current, the more voltage you're gonna get. Okay? Let me do an example here so you guys can see. Okay, so based on this formula, if the let's say the current changes 5 amps per second, right? And the inductance is, let's say, 10 amps, 10 henries, right? That is the induced voltage. Then would be 10 times 5 would be 50 volts, right? Now, what happens if the change in current it's not that. Let's say it goes up to 15. So 10 henries times 15 amps per second. Now see, the voltage went to 150 volts, right? 10 times 15. As you can see, the voltage is proportional to the rate of change of the current. So the higher the current changes per unit of time, in this case second, okay, the more voltage you get. The same thing will happen if the current, instead, let's take this right there, okay, use 10 henries multiplied times 5 amps per second. We know that this is 50 volts, right? What if the inductance changes and goes up? Let's say the inductance goes up to 20 henries times 5 amps per second. Now 20 times 5 will be 100 volts. See that? So based on this formula, this is a simple base multiplication, right? They're on the same level. So therefore, if the inductance goes up, the voltage goes up. If it goes down, then the voltage goes down. If the rate of change of the current goes up, then the voltage goes up. If this one goes down, then this one goes down. So what they're saying there is that the voltage is proportional to the inductance, and is also proportional to the current change. All right? Okay. So in self-inductance, energy can be stored in an inductor because of the magnetic field. And the energy that is stored in an inductor is calculated using this formula. It's going to be the inductance of the inductor times the current that's being forced through the inductor, square, okay? All this divided by 2. And the energy is given in units of joules right here. Okay? The inductance is in henries, and the current is in amperes. This is the current square, so that will be square amperes times henries. That gives you joules. So inductors, they're very unhappy devices because they don't like to receive current through them, changes of current. That's why when the current on the inductor changes, this current that is being applied through this source, when the current changes, the inductor generates a magnetic field that opposes the change in current. Okay? So, and the polarity of the voltage induced by this magnetic field is the opposite as the current. It depends on the direction of the current. That is the variation of the current, right? So when this one increases, the VL, or the induced voltage, has polarity that opposes the increase in current. And when the change in current decreases, then the voltage has opposite polarities to oppose the decrease. In other words, this guy is never happy. If the current that you put through it increases, then this one generates a magnetic field that opposes that increase. Okay? But then if you say, well, I'm going to decrease it, then it also generates a field, a voltage that opposes that decrease. Okay? In either case, the change in current is opposed by the induced voltage. All right, so I'm going to stop here, and we're going to stop the recording here, and then I will continue with another recording that we're going to start, in which we're going to start talking on mutual inductance. Okay, this is when we have two coils near to each other. Okay, so for now we're going to stop here. We're going to take a break, and please review the problems on the book and the problems that we solved during this lecture. Thank you for your attention, and I will be back with a second part of this chapter.